So good morning. This one's on plotting the motion of the tello drone in X, Y, and I've called it minus Z because on the drone Z is downwards positive, so we need to nice to have graphs going upwards. So I've put minus Z in there. And we look at the drone, it's got some X, Y, Z coordinates here, and when the drone starts up, it remembers its orientation, and any speed or velocity or signal that's generated using speed for the angles relative to the initial axes that it set itself up in, which means that if it yaws, then the forward motion of the drone is not x now, it's going to be x times the sine of the cos of the yaw. But as it turns out, this is a handy feature of the drone. It makes it actually easier to plot out what it's doing. One of the issues with the drone is the signals that come off the sensors are quantized, so they don't come off as a nice smooth graph but like little sawtooth values. This is a typical value for a height, and this is a typical value for a speed. So if we look at the graphs that we can produce, this is one I've made now in the program. As the x speed, we integrate the x speed to get the x distance, get the y speed, integrate the y speed to get the y distance, get the z speed, z positive, so this is minus z really, integrate the z, and we get the height. This is where I put a yaw into the drone at about 8 seconds. So there's a yaw about 40 degrees, or 45, should have been 45 degrees. So the drone's gone along in the x, and then it's yawed by 45 degrees and then go along that trajectory there. And so that's the motion of the drone in x, y. And you can also get a 3D plot of it as well. So you can plot x, y against z to get a 3D plot. And if you look at what's happening here, it's a matter of interest. It's got the x motions at the start, so there's an x motion and no y motion, so that's the x motion on there. And then it starts to do some rotates by 45 degrees. It starts to go off this way, so it's got some x motion and some y motion. So this represents now the x motion. This part here represents that motion, and this part here represents that motion, and this part here represents that motion. So by integrating these two signals, we get these parts here. If we plot that against that, we get this nice almost straight line at 45 degrees, which is what we're expecting to see. So, oh, it looks quite promising. Now let's have a look at there's a program now that does all this. So I'm going to go through now each part of the program, describing what it does, and then you can have a look at the program, run it, and also start to understand it. So the first thing it is, get to take off, and then we measure the yaw, which is called theta, and we start a couple of timers and values off. That should be timer there, but anyway, some mistake in there. So r equals rise, take off, and then measure this theta star. The orientation of the drone is set by a gyroscope. So if you change it round at the start, it will give different values for its orientation. And I want to look at the change in orientation. So I'm working out the start angle before it kicks off. That gives me the initial values. Now r comes back as 3 values. You've got the orientation in x, y, and orientation in z, if you like. That's like which is like the yawing. It's got the pitching, which is the orientation in y, and it's got the rolling, which is the orientation in x. So 3 values come back. We're not really interested in pitching and rolling on the drone, but we are interested in the yawing, which is this one. So that comes back as a vector with 3 values in. So you can then have start theta start 1, which is the yaw, theta start 2, which is the pitch, theta start 3, which is the roll. And then I start off a timer called t-run1, so tick starts off the timer. I set a value of t0, which is the time in the program, and n is 1. I write into an array every time we take a reading, and the first value is 1 minute, the second one is 2, third one is 3. So n is used like an integer number to increase the number of the array, and put numbers into it so we can plot them out later. So getting data from the drone, we've got height is equal to read height r. That just returns height. There's no, it's just a single variable. Angles though, you do read orientation r, you get 3 angles back there, which I just mentioned. And then if you do a read speed, you get 3 speeds. That's the speed in x, speed in y, and the speed in z. So speed 1 is speed in x, speed 2 is speed in y, speed 3 is speed in z. Theta 1 is the yaw. So bear those in mind, because going to be using those in the program. This isn't in the program, this is just telling you how you can get read data using these read height, read orientation, read speed. So this is the next little bit of code now. So it's got move forward, which is going to move forward r, a distance of 1 meter, and this wait till done false means we can run some MATLAB code whilst it's doing this. If wait till done is true, it just runs this code and waits until it's done that job before running on. But if we do wait till done false, we can run some code simultaneously. This is a while loop here now. It's not that complicated. So while toc is less than t-run is less than 8, so tick has started off t-run, and toc is its current value. So whilst the value of t-run is less than 8 seconds, it means for the first 8 seconds it's going to do this task here. It sets ts as tick. Tick is a new timer now. When it gets into this, it sets ts as tick. It then measures speed and measures theta. Now this line is a special line I got from MATLAB Command Center, and sometimes the data coming back from the drone isn't correct. If it isn't correct, it crashes the program. So this checks now that the data's okay. You don't have to worry about it, but it's this line that checks the data's okay. If you don't have this line in, it doesn't work. Well, it works sometimes and not others. Then, as it's running, it's done a speed signal. So if I put sx is speed 1, sy is speed 2, and sz is speed 3. So it's storing now into 3 arrays, sx, sy, and sz, the forward speed will be x, y, and z speeds. And it's also called A for angle. It's turning out the angle of the drone, and that's going to be the start value, which I got at the very start, minus, that should be theta there, shouldn't it? We need to make that a bit bigger. Minus theta 1. So theta 1 is the measured one we just measured now, the yaw, and this is the value of yaw at the start, so as we know what the change is then. Then makes the time step equal to toc of t. So it's come into this program, it's run all this code. That takes a while to run that code. It says work down on the time it takes to get from there to there to run that code. It's going to be toc of ts, and that's going to be our time step. Then it makes the time, because the current value of time plus this time step, so it moves our time on, and it writes that value of time then into the array, and then it moves the array on as well. So next time we write to the next part of the array. And that's a bit of code now that stores speed and theta as it moves forward a distance of 1 meter. Next part of the code, I pause the drone for 2 seconds, and then I turn the drone by 45 degrees, and then pause again. Now, I didn't want to put these pauses in, but if I didn't have the pauses in, sometimes it would run through this code without doing it. It's a bit of a nuisance. So I had to put these 2 pauses in. I'm not sure why that's happening. I've not used this drone much, so I'm not 100% familiar with its bugs and the things it'll do and don't. But I find if I put a pause there, so the drone will move forward for a meter, pause for 2 seconds, and then it'll yaw by 45 degrees, and that's what this simply does. Turn R, degrees to radians converts 45 into, so it works in radians, the drone. So it converts the 45 degrees to radians and turns that many radians. If it was negative, they'd go in the opposite direction. Then it now moves forward again. So this is exactly the same code as we had before here, but this time we've got t run 2 is tick, and this is t run 2 is less than 6. So t run 2 is a timer, which it starts off there, and then whilst the time is less than 6 seconds, it stores the data in exactly the same way. So this bit of the code is identical to what we had before, really. So we have to go through that one, but it stores values. Then, having done that, then it moves up a meter and starts up a third timer, and it does this for 5 seconds. Again, that code is the same code as we had before. So you can see a lot of this is just having some command here, and then this is standard code. The only thing you need to control is how long you run it for. So you can set off a timer and use that timer then to control the time. So this is 5 seconds it'll do this, but it'll go up for 5 seconds. Now, the next thing I want to talk about is the drone doesn't have a method of measuring x or y. It can measure height, but it can't measure x and y directly. So what I've done is, imagine some variables as speed. If we integrate speed, we'll get distance. So if this was a speed graph here, the area underneath will be the distance travelled. Now, because it's a digital computer, the values are measured every so often, every time step. So in the real-time sense, we'll know now to work out this area here, we could strip it off into little strips. So we know that length there, we know that value. We could say that could be like a little box to represent some of the area. Then next time we could take that box and then that one out. So we added up those 4 boxes, we'd get an approximation now of this area, which would be the integral of speed. In other words, if we add those boxes up, we'll get the distance travelled. As we add each box up as we go along, we get the current distance travelled. So this is the thinking now behind this simple line of code, which says that the x distance is equal, currently, is equal to the old x distance, because you're going to add these together, plus, and then I've got a fiddle factory of 1.4 in, and this parameter here is the strip width here. So that's going to be the current value of time minus the one before, so that's that width there, and this is the current speed, so that's that distance there. So by multiplying that by that, we get that distance, we get this area of that curve. Let's say we're doing this one, so we've got this one is that value there, and then if we take the current value, so from there to there will be that distance, and this value here will be that distance. So we multiply that by that, we get that box, then add that box to that box, that will be the total distance travelled by the drone. Keep on doing that as you go along, and we'll get an next estimate. So that's what this code is doing. It's doing numerical integration of the speed to get an estimate of the distance travelled. Now this shows you, you have to actually make the step length small in this method, and you've got a curve that you're following. So if the step lengths are big, the approximation isn't so good, but if the step lengths are small, then the approximation becomes quite good. And in our case, the step lengths are very small, so we can this isn't going to work too bad. This is the code then that it lands the drone once it's done its flight, having stored now values for, let's move this up a bit, for SX, SY and SZ. They're all stored away. So the first thing it does is works out the length of the vector that we generated. All the vectors are the same length, so LEN works out the length, and then it makes 3 vectors then, which are filled up with zeros, of this length. with a 1 in there, and then it then runs this loop. Then it's got these values here, so it applies now the technology that we had here, applies this thinking now to the x, y and z loops, and then that gives us then x estimates, y estimates and z estimates. And this code here, you don't need to change this code as long as you roughly understand it. The only thing you might want to do is change this number. To put a number of 1.4 in here should be 1 really. I have to put 1.4 to get realistic values for the x estimates, otherwise they're coming out a bit low. So we integrate the speed. It wasn't seem to be as travelling as far as it actually was. But you might need some adjustment on that number, unfortunately. It's a bit of a fiddle, but it does work up to a point. And the last thing now is we need to plot out the graphs. So I'm using a command called subplot, and subplot works like this. And the first number is the number of graphs you got that way, and the second number is the number of graphs you got that way. So 3 by 3, 9 graphs. Then the next number is the graph number itself. So the first graph is number 1. This is number 2. That's number 3. That's number 4. That's number 5. Number 6. Number 7. Number 8. And number 9. That's never labelled. So next 3 by 3 plot. Then that number there tells you which plot you're messing about with. So this goes subplot 311, and it does a plot time against speed x, and then you can put a title in. Then the next one's graph, that's this one here, speed against time. That's a speed against time plot. Then the next one is graph number 2, so it's this one here. This is going to be speed in y against time, so that's going to be speed in y, and that's doing the sy. Then the last one is sz, so they're the speeds along there. Then we've used this bit of code here now to generate x, y and z estimates. So the next 3 are doing the x, y and z estimates, so they go along that way. And then we then have a graph plotting yaw here, number 7. So plot 7 is doing A is the angle, so that's plotting the yaw. Then I've got another one which plots x against y. So this just plots, hasn't got time on, it just plots x estimate against y estimate. And then the other one I've got is quite nice, plot 3, plots in 3D. And if you do x, y minus z, you'll get a 3D plot down here. So then this gives us you can change this if you want, but it gives you a way of seeing what the drone did. So this is its x speed, y speed and z speed. This is x movement estimate, y movement and z movement. This is its yaw, this is its xy motion, and this is its xyz motion here. So that's the complete program. So it's got about 150 lines in, but to modify the program, all you've got to do is just add in, and to do some extra tasks, you just add in some of this, what type of move you want in there, and a bit of code like that. So it's not that hard to modify. If you want to do a turn, just put a bit of code like that when you want it to turn. So if we go to the program itself now, then this is the program. I've called it your tello program test for some reason, but it's a standard program. It's all that code that I've just discussed is in here, exactly the order that I've discussed it. But it's also got the extra thing of this catch exception thing. Now the only drawback of putting this in is if the program crashes, it doesn't tell you what line it's crashed on, so it's hard to find to debug. So if you can't debug it, you could remove this bit of code and remove the try. On the top here, remove the try, and then when it crashes, it'll tell you what line has gone wrong. But the drone then will, when it crashes, will fly, and you won't be able to land it. So then you need to go down to here and type in land, say R like that, and then it'll land the drone. Otherwise, it'll just fly forever, which is a bit nuisance. That was the advantage, remember, of putting this try code in. It's not going to like this now because it's not even taken off. Anyway, it's not going to like it at all. Don't know what it's done. It's crashed. Control C will stop it from. There you go. So let's have a go now at flying the drone and seeing all this happen. Right, so here we go. So if I now click on run, it's going to run the drone, and I'm going to try and get the video picture at the same time. So I'll click on run. There you go. And it's taken off. Now it's going to move towards us about a metre. Here it comes. Now, stop about that. It's not going to yaw now at 45 degrees. There we go. Now it's going to go forward. It's going to go too far. That's going to go up. There's off screen probably, on the screen. It's going to come down in a second and land. There we go. So that's its motion there. And it's now, as it ran, it generated this data for us. So here's the speed. So it went, yaw was 0, and it was going in X versus, it's gone like about a metre, which is what it's meant to do. And that's that signal, that's the speed signal that made it go about a metre. Then it's yawed, then at this point it's yawed by about 45 degrees. And so then it's gone the X a metre, and it's yawed 45, and it's gone off now at 45 degrees in this direction. And to do that, it needed a bit of speed in the, speed in the X and speed in the Y, and so it then moved in the Y direction as well. And then it's going on. It's not quite perfectly straight, but it's not too bad. So it's gone along there and at 45 degrees to some other point here. This is the Z then. At this point then it's gone up, and this is the change in Z, and that's the change in Z signal speeds to get the change in Z there. And then this is our 3D plot, and this one now we can rotate. It's quite cool. We can rotate it as we fancy, and we can see what sort of went on. So you can see it's going along, and it goes to 45, and then it goes up, and it goes up the metre. So it's not far off really. So you can see, got this extra zero, and rotate it right round. Let's control it now. It's not easy to get a nice. I've messed it up now. Here we go. That's better, isn't it? So I didn't do along there. It did go quite straight ours, but it seemed a bit wobbly. But that's because of. It's not too bad then. That's along there. It's going up a metre. So that gives you then the graphs. And if you go on to File and Copy Figure, you can then print the whole graph then into Word. So if we then went and opened up a little Word file. Find the word somewhere. There you go. Open up a Word file, and then do a paste. Then I've got the graphs in there, and you've got your thing. So notice what's going on. It's doing an X motion here, so it's an X motion. Then it does a yaw, so then it's doing in order to go off this direction, it's got some X motion and some Y motion. So that's the X speed as it went along. So it went along there, that's the X speed. This is the Y speed. And if we integrate those, that's the X and the Y motions. These are a bit big. They're not perfect, these. The X is a bit big and the Y is a bit small. But that's the motion it did. And then if we plotted X against Y, we get that almost straight line motion as it's going at 45. Then it's a bit later, it did a bit of a height change. And that's the height change there. So it goes along that way, and then up. And you could obviously make this more complicated if you wanted to as well. So that's the program. What else am I going to say about the program? These are the X estimates, remember? And this is the subplots plotting down here. And that's the complete program. So this allows you now to move the drone round, and as it's moving round, you can plot its X, Y, and Z motions. We can also do, and it's yaw as well. You can then also plot anything you fancy really. It's just up to you, but you can plot X versus Y, you can plot 3D, plot anything you like, and you can make as many graphs here as you like. The trouble is you make this bigger, it's obviously the graphs get smaller inside, so that's a bit of a nuisance, isn't it? But anyway, this is live, because you can tell it's live because I can move this box, 3D box around, and it's still, you can see it's wasn't quite perfect. And some of them I've done, this isn't such a good one, I did a perfect sort of line there, and these numbers are quite good as well. Oh yeah, the point I was going to make was, these numbers aren't perfect, and they come off these numbers here, these numbers, so you might need to tweak those numbers slightly for X, Y, Z. I've not run this program more than about 5 times, so I haven't got enough experience of it yet. But these numbers, if you tweak those numbers, you'll get different numbers on X and Y movement. So you'll know what X and Y movement you're expecting to get, or what the real thing did. You could tweak those numbers slightly to get slightly more accurate results. The height doesn't seem too bad, does it? It's meant to go to 1, and it's more or less gone to 1. And that's more or less gone to 1 there as well, which is what it's meant to do. This is meant to go to about 0.7, that should have been about 1.7 there, so it's gone to 2. So this one's a bit big. I don't know what this one is. We'll interrogate the screen, Nick. Will it interrogate it? 0.5. Interrogate the screen. So this one's a bit light, isn't it? This one's a bit light, so that might need a bigger number. This one's a bit not too far off really, but it's a bit off. It's not going to be perfect this, because we're integrating these signals here, which they're not that good a signal really, but we are getting fairly good values for X, Y and Z from the program, and it looks nice. And remember, one of the things you need for your final year project, you can't just have a drone and say it worked well. It'd be much better if you've got graphs showing what it did, because then you can talk about the graphs, and the graphs have meaning to people. So that's why I think this is the first step in the right direction. So what you need to do is master just moving the drone using just move and rotate, controlling on distance and speed and time, so you can control your drone. That'd be the first thing I do. The second thing to do is master these programs and be able to do it, make it do various tasks and plot them out. And once you've done those things, then you've then got control of your drone, and you can plot out its motion. And then when we've done those things, then we can then move on to the next stage, which is integrating into it the vision system. So the next thing we can do then is to add in the forward-looking camera, and maybe take some pictures and use the camera then to make it do something more intelligent. Now what we do, because there's a few students in the project, we'll have to use the camera in different ways, but the basic use of the camera then would be the thing to develop up to Christmas. So by the time we get to Christmas, you can control the drone and plot the drone, and you can make some elementary use of the vision system. And then after Christmas then, you can use the vision system to make the drone do something a little bit more smart, a little bit more intelligent. That would be we'll have to define a different project for everyone. Can't have everyone doing the same project. But there's lots of things you can do with the vision system to make it do stuff. So that's our final thing. And there's some quite simple little vision system calls we can make, and I've got vision system examples, and I'll try and show you some vision system examples running, but we don't need those until closer to Christmas. Okay, so hope you found that useful, and speak to you soon.